The aim of this project is to design a collapsible pavilion using Mura folding, designed for modularity, adaptability, and quick assembly in temporary or mobile architecture. Why Mura pattern? The Mura pattern enables durable, adaptable folding, allowing dynamic spatial configuration suited to diverse architectural and design needs. This is the folding unfolding behavior of the pattern. First understanding with this system was that it is mainly about the mountain and valley edges of this geometry. The first prototype combined scissor mechanism with the Mura fold using rigid, precise panels, scissor linkage on each module with cables at their tips, enable manual folding, mimicking the motion of deployable umbrellas and expandable screens. In this inference was that deploying the system required pulling multiple cables per module, which proved inefficient and impractical at a 1:1 scale, making manual control of individual components tedious and unfeasible for real world applications. This feedback pushed me to think, can one input lead to a collective movement across the module? To improve the previous iteration, I introduced cable based actuation at each vertex of the Mura fold geometry, enabling synchronized folding. This system enhanced control, making transitions smoother, more responsive, and precise by translating manual force into coordinated movement. To address the issue of individual control, I integrated fabric between rigid panels, forming a three-layer sandwich. The fabric acted as a flexible hinge, enabling all modules to fold or unfold collectively, creating a unified and responsive surface. Though the fabric system enabled unified internal folding, the absence of edge mechanisms hindered controlled deployment, making large-scale operation unreliable, inconsistent, and dependent on manual intervention. This feedback pushed me to think, how can whole geometry fold unfold which is similar to how it is working manually? To tackle that, I refined the scissor mechanism by consolidating it at the edge of the module. This edge-based system acts as a master control, driving the folding motion of the entire panel, similar to how a book cover affects all pages. However, after prototyping and discussion, I had to confront a real-world issue. While fabric worked brilliantly at model scale, but at 1:1 pavilion scale it lacked the structural strength to resist wind or tension loads. So the challenge now became, how do I retain this one-point control system while replacing fabric with a more structurally stable material? To tackle that, I shifted from fabric and edge-based scissor solution to a direct hinging mechanism at the central mountain valley fold, simplifying the design by using metal hinges as primary connector between flat panels. Folding failed beyond the first panel as the second rhombus-shaped panel resisted folding. Upon analysis, I found that extended bolt heads act as an obstruction, preventing full articulation. This failure emphasized the importance of flush integration in deployment system, especially in tight folding geometries. To address the obstruction, I replaced bolts with rivets for flush panel interaction. However, the structure still failed to fold due to the second rhombus-shaped panels tilting perpendicularly, caused by material thickness and hinge gap mislegging the panels. Learning from iteration 6, I addressed the core issue by adjusting the geometry itself, reduce the size of the second panel by an amount equal to the size of the material and the thickness of the hinge pipe. Reducing panel size caused insufficient space for hinge placement, so I extended the central strip, adding protrusions to support hinge connections. This dimensional adjustment allowed the entire system to fold seamlessly. These are the drawing of module. Size of module is 1.8 meter by 1.8 meter when it is completely open, and 1.8 meter by 16 centimeter when it is completely flat pack. This is the provision for cable in central MS strip. Module to module design. In Mura, mountain and valley folds are relative to observer's orientation. Flipping the pattern 180 degree or viewing it from the backside swaps the folds. For module connections, I use the same central strip joined from the backside, allowing easy assembly and disassembly with a consistent form. This new central extension introduced another issue. The cables now clash with the extended plates. This could no longer run straight from hole to hole. To tackle that, I revisited the folding pattern of geometry. I observed that valley fold move along the y-axis while mountain folds move along the x-axis. To resolve this, I introduced a threaded rod parallel to the central strip, supported by eye bolts, guiding the x-direction motion for easier opening and closing. The folding and unfolding of the geometry is controlled by rotating the central MS threaded rod, which also acts as a locking system. Currently, a low pitch rod is used, requiring more rotations. Switching to higher pitch threaded rod could reduce the rotations and improve the deployment efficiency. How it will assemble disassemble on site. First, modules will be placed on ground. After that, modules are connected by central MS strip and rod. Rotate the rod to unfold the structure, lock the structure, and lifting up the structure by pulley mechanism. This is the exploded view and design resolutions. This is the 3D view and module specification. Material is mild steel box section, size of 18 mm by 18 mm. Weight of one module is 17.5 kg. When module is completely open, the size is 1.8 meter by 1.8 meter, and in flat pack condition it is 1.8 meter by 16 centimeter. Infill material is polycarbonate sheet. Hinge size is 750 millimeter. Material of center strip is 2 millimeter mild steel pellet sheet. Thank you.